Well, hello everybody. I'm Nick. I'm with the University of Louisiana satellite team. And the satellites we build and launch are called CAPE, Cajun Advanced Pico Experiment. My call sign is K5QXJ Juliet. And you can see my email and the URL of our satellite team. Today we're going to talk a little bit about modulation. Modulation is how we impute information into a radio so that we can send data from our satellite down to our Earth station. So let's get started. So the first thing we need is we need a transmitter and a receiver. And today we're going to simulate our transmitter with a flashlight. Actually, a flashlight is a real transmitter. It emits electromagnetic radiation, and our receiver today is an eye, because it responds to the radiated energy emanating from the satellite. So let's show you. So if I point this satellite toward the camera, when I get there, you can see the bright light, and notice that this light carries no information. And this light, this wave coming from this satellite, we call a carrier wave. And remember, a carrier wave contains no information. So now my challenge for you is, how can we make this light carry information? Well, let me demonstrate. The flashlight's a little slow. For the Boy Scouts amongst you, will immediately recognize this is Morse code. And you also might recognize is that 3 short flashes, 3 long flashes, and 3 short flashes are the symbols for SOS. And SOS is a universal distress signal. So what did I just do? I took that carrier wave and I changed the amplitude. And by changing the amplitude, I actually encoded information onto that carrier. Well, another word for change is modulation. So by changing the amplitude, I now have impressed information on that carrier wave. Guess what? We call this amplitude modulation. And you guys are familiar with amplitude modulation, AM radios, because almost every vehicle today has an AM radio. Parenthetically, us hands might call this ancient modulation. So let me show you another way to encode information onto a carrier. So again, I'm going to take the flashlight and face it toward the camera, and then I'm going to filter out some waves and show you. So for example, we might want to say if we see a red signal out here, that could be represented as a 1. If we saw a green signal, as shown here, we could say that could be represented as a 0. So essentially, what did I do? I changed the frequency of the carrier wave. And we would call this frequency modulation. Again, most of you guys who own vehicles play FM radios every time you get into your car. So let's look at some sine waves. So first of all, here's a sine wave. So what are the characteristics? How do we describe sine waves? Well, there's 3 characteristics we use. The first is amplitude, the second is frequency, and the third is phase. So remember, in our first example, we encoded information on that carrier wave by changing its amplitude. So let's kind of look at what that might look like. Well, by the way, in the on-off deal, we showed digital waves, but we can also send amplitude information. So let's, for example, say we have a sine wave, and we want to put that onto our carrier. And this sine wave, let's assume that it's 1,000 hertz. And our carrier now, in typical satellite carrier radio, is a frequency is 400 megahertz, many orders of magnitude higher. If we took this amplitude sine wave, 1,000 hertz, and pressed it onto the carrier wave, we would wind up with a waveform that looks like this. And if we have an envelope detector, we can recover this 1,000 hertz sine wave by looking at the amplitude of the envelope. So let's now move on to frequency modulation. So again, if we have a sine wave, say 1,000 hertz, we have our carrier at 400 megahertz, and this time we change the frequency of the carrier so it looked like this. So at some point we make the frequency of the carrier go up, and if we then at certain points of the waveform we make it go down, we change the frequency, thus the name frequency modulation. Now to recover this sine wave, all we have to do is detect the change in frequency of our carrier wave. All right, and we do this with a circuit we call a discriminator, which essentially detects the change in frequency. So now let's talk about digital signals. So if we wanted to send a digital signal, and a digital signal is essentially ones and zeros, all right? And notice that we could say that a 1 is an increase in frequency, so our carrier frequency would show increase in frequency. A 0 could be educated as a negative change in frequency or a flawless signal. So look, here we go. Now we give this the name frequency shift key. I want to talk to you about another way to impinge information on a carrier, and one of the ways we describe a sine wave is by its phase. So if we change the phase or modulate the phase, we could say that a 1 would be represented when the phase is 0, and a 0 could be implemented as 180 degrees of shift in phase. So notice, look, that the sine wave shifts in frequency. Now I want to back up a little bit and show you something that I failed to mention. I want to go back to sine waves. So, okay, notice that this sine wave contains no DC terms. In other words, this is a pure sine wave, and there's no DC component in this thing. But when we send digital signals, for example, this modulating wave is DC. So to make radios respond to DC, we have to do something different, and that is we either change its amplitude, its frequency, or its phase. Okay guys, that's it for me today. See you next time.